What's up, students? Hope you're having the best day of your life today. Today we are going to talk about SAT physics formulas that you need to memorize by the specific topic, okay? And what I mean by you need to memorize them is about the SAT physics exam. You are not given a reference table. You are not given a formula sheet. This is one of the major downsides, and I feel like something that keeps students from taking the exams when they find out they have to memorize formulas. It's not that big of a deal. While you're studying and while you're doing all this extra work, guys, a lot of these are beginning to become second nature, and it's not going to be that big of a deal. So first, guys, let's just go through the kinematics formulas. Now, on the risk of dragging this out too long, guys, I'm just going to go through the formulas, their variables, and maybe like a little trick or something that you could use to remember how to use these things. The first one is going to be the average velocity formula, and that's going to be the displacement over time. And this is flat out the definition of average velocity. And when acceleration is constant, we know that the average velocity is also going to be V1 plus V2, or V initial plus V final, over 2. Just like you'd find the average of any two things. You would sum those two things up and divide by 2. These are the average velocity formulas. The definition of acceleration is the acceleration is equal to the change in velocity over time. I said this is the definition. Whenever there is a change in velocity, there must be an acceleration. And whenever there's an acceleration, there must be a change in velocity. The next formula is when you do not know the final velocity of an object, we can say that the displacement is equal to the initial velocity times time plus 1/2 the acceleration of that object times time squared. So a couple of things, don't forget this squared. Oftentimes people will do that. And this little circle right here means not, it's just an initial velocity. And it's also worth noting that change in position, also known as displacement, is the final minus the initial, just like you'd find any other change. So this right here can be rewritten to say that x minus x naught equals v naught t plus 1/2 a t squared. Oftentimes we just call our initial position 0 and this term would go away. The next formula is awesome. If you do not know t, you can know the final velocity squared is equal to the initial velocity squared plus 2a delta x. So once again, this is when you know the final velocity and the initial velocity of an object, but you don't know how much time has gone by. The last one, we can kind of just take this formula right here. If I know that the change in velocity, just like here, is the final velocity minus the initial velocity, I can rewrite the acceleration velocity as this. So I'm just going to derive this equation. It's not really something you need to memorize, but right here, I could take this and say that if I know the final velocity and I don't know the displacement, I could say the final velocity is equal to the initial velocity plus AT. So that's kind of like, this is when you don't know t, this is when you don't know displacement. Those are the formulas that you need to memorize for kinematics. So next will be for dynamics, and this is when we're going to start to bring in some forces and start to explain this motion using forces. The most important one, guys, is Newton's second law, and that says F net equals ma. You might see this written as this, where F is a vector. This is the same as saying F net. This is the sigma sign. It means summation. And that's going to be equal to ma. So you might see them just noted either way. They mean exactly the same thing. Another way that we can write Newton's second law when it comes to Earth is we could find the weight of the object, aka Fg, as m little g, where g is the acceleration due to gravity. So if I just get rid of this, we could say that W equals mg, or we can say that the force of gravity on Earth is mg. So this is force equals ma, where this is the acceleration due to gravity on Earth. The force of friction is equal to a mu. So this is a mu. Force of the normal. Remember, there is no formula for the force of the normal. You must solve for the force of the normal. And a lot of the times we're going to use Newton's third law to find the force of the normal, but this has to be solved for. And we must remember that mu can be static, meaning the object has not moved yet. So this is going to be the force required to get this object moving, or it could be kinetic. And that mu will be used if the object is using. And sometimes they'll just do this mu s or mu k. It really just depends on your notation. The next one is going to be the definition of momentum, okay? And momentum is going to be conserved when there's no outside net forces acting. So P is going to be equal to the mass times the velocity of that object, where this right here is momentum. And if you want to change the momentum of an object, you must add a force for a certain amount of time. Now, this force times a certain amount of time has another specific name, impulse, that sometimes, depending on the book you're reading, you'll see denoted as a capital J. So sometimes you'll see delta P equals F net T, which also equals J. The next topic is going to be work, power, and energy. So the first formula is going to be for work, and that is equal to the force cosine theta x. Now, guys, a lot of times in textbooks, you'll see this, fx cosine theta, and I want to tell you, I write it like this because this reminds me that theta is the angle between the force and the displacement, the movement, okay? So when you see it like this, it's not a big deal, but we have to remember what this theta means. Now, if you're on a horizontal surface, the angle between them is 0, and the cosine of 0 degrees is 1. So on a horizontal flat surface, we can just say that work equals force times the displacement. If there's no displacement, then there's no work done. The definition of kinetic energy is equal to 1/2 the mass times the velocity squared. Once again, don't forget the squared. I see it happen all of the time. Gravitational potential energy is written with the variable capital U G. Sometimes I'll see it written as just PE gravity or PE earth. It doesn't really matter as long as you're consistent, but traditionally you're going to see it a capital U with a G, and that is equal to the mass of the object, the gravitational acceleration, which on Earth is going to be 9.8 meters per second squared, or 10 on the AP level. That is going to be multiplied by a change in height. This change in height is very, very important because when we find the potential energy, we need a reference position, and then we are going to go upwards. The only way to change an object's gravitational potential energy is to go straight up. It does not matter if you take a swirly path. It's only from the initial position here up to the final position here. This is delta H. That's all that matters. We don't care how it got here. It's from the start to the finish. Now, when it comes to energy, a change in energy is equal to the work. So work is actually defined as a use of energy, which we talk about in our work video. But the change in energy is defined by the work. If you change energy, work must be done. So this is a nice little relationship right here that needs to be memorized as well. When energy is conserved, we say that the energy total. Now, energy total is sometimes referred to as mechanical energy. So the mechanical energy is equal to the kinetic energy plus the potential energy when energy is conserved. When energy is not conserved, we'll add other variables like the work taken away from non-conservative forces like friction. And the last work, power, energy is that power, and power is the rate at which we do work. So the amount of work done divided by T. If we want to derive this even further, we know the definition of work. Work is displacement cosine theta divided by T. That is another way that you can find power. And if you want to take it even one step further, we know that X over T is average velocity. So the power is also equal to F, average velocity, cosine theta. Like I said, 9 times out of 10, theta is going to be 0. It's going to be on a horizontal surface. So if you can get rid of these whenever we're on a horizontal surface and just say that power equals F displacement over T, or FV cosine theta. For uniform circular motion, the first thing we're going to do is that we're going to apply Newton's second law for motion. And we know that Newton's second law is F equals ma. But now that we're moving in a circle, we're going to see that FC is equal to mac. Now, something to remember about FC, guys, this is not an individual force. FC is the net force that acts towards the center. So just like you'd solve for F net in dynamics, you must always solve for FC. Now, we also know that AC is going to be equal to V squared over R. So I can derive and rewrite this as FC equals mv squared over the radius of that circle. This is often how you're going to see it written. And with some other things that I see in circles, guys, we remember from kinematics that the average velocity is a displacement over time. Well, guys, remember that the distance in a circle is circumference, okay? So we can also now say for an object moving in a circle, the average velocity is 2 pi r, or pi d, divided by time, the circumference over time. If I go in a circle, this is the distance, the circumference. So I often see that. So this is the average velocity formula for something that's moving in a circle. Okay, next is going to be torque and angular momentum, guys. Remember that torque is the result of a force at some distance from a pivot point. And that force must be perpendicular to the lever arm. Sometimes it's not, so we must find a component. So I can just say that the torque is equal to some force perpendicular at some lever arm R away from the center. So here's a pivot point. Here's some sort of lever arm. This would be a perpendicular force at some R away. That's how I'd find torque. Because sometimes that force comes in at an angle, I also rewrite this as the force times the lever arm times the sine of angle between the lever arm and the force. I've done a ton of videos, guys. This is a very confusing topic. Please look at the angular momentum. Look for a rod video. I'll try and link it at the end, please, or I'll put it up in the card above. If you're not sure what this really means, take a look at it. It's very important. Next, for springs and simple harmonic motion, there's a couple formulas that we need to understand. And that is that the restoring force on a spring, so the force that a spring puts on itself to return itself back to an equilibrium position, like where a force is just straight chilling without any forces being applied to it, there is always going to be a restoring force that wants to bring that spring back to that position if it's stretched or compressed. And that restoring force is dependent on its stiffness, and we call this the spring constant or the K constant. This is unique to each spring, and it's usually given, or you can solve for it, times the distance that it is stretched or it is compressed. And this is known as Hooke's law. The other thing to understand is when you stretch or compress a spring, it gains some sort of potential energy. So we can call this US, just like we call gravitational potential UG. Sometimes you'll just see it written simply as PES, the spring potential energy, is equal to 1/2 that same spring constant times the distance it stretched or compressed squared. Now, guys, this looks a lot like the kinetic energy formula. Please don't get them confused, all right? This is the potential energy formula for a spring as you stretch or compress it depending on its stiffness. For simple harmonic motion, guys, the period is how long it takes to complete one full cycle, as you know. And the period of a spring is equal to 2 pi times the square root of m, the mass, divided by k. Now, this is the mass that's causing the motion, the simple harmonic motion. You'll often see this formula used when we hang a mass from a spring and it oscillates up and down. This is the K constant of the spring. This is the mass that's being hung on the spring. And the period of a pendulum, something else that frequently performs simple harmonic motion, is the same 2 pi divided by L over G. And to remember what's under the square root sign, guys, just remember the things that affect the period of a pendulum and the period of a spring. The only thing that affects the period of a pendulum is the length of the string and the gravitational acceleration here on Earth or whatever planet you're on. The only thing that's going to affect the oscillation of a spring is the mass that's hanging on that spring times the stiffness of that spring. The last period formula that you'll see for everything, period is equal to 1 over F. You see this in a couple different topics, but most commonly in simple harmonic motion. Gravity, you're going to get away pretty simply, guys. Gravity, Fg, is equal to the gravitational constant that's going to be given times mass 1, mass 2 over the distance between their centers squared. This is going to be used to find the force between any two masses. Here on Earth, that can be simplified as Fg. So this is also called weight. The force due to gravity is called weight. Here on Earth, I can say mg. So essentially, little g is equal to the gravitational constant times the mass of the Earth divided by the radius of the Earth squared. The electrostatic force is going to be equal to K, Q1, Q2 over the distance between them squared, which looks a lot like this gravitational formula. Also, we're going to have the force that a charge feels when it's placed inside an electric field. So the force that a charge feels when it's put inside an electric field is also going to be something that you need to understand. And this is going to be the electric field strength. When I take that electrostatic constant, I multiply it by the charge at a certain distance from the charge. This is going to be the formula to use. The potential difference, delta V, is equal to the work done by a charge. All right. And this, once again, this WE is a work done by an electric field. We can also rewrite this as FE, the electrostatic force, divided by Q. Next is the electric potential due to a charge at a distance from the charge. So here is the electric potential. That is K Q over R. Very similar to this formula up here. And the electric field strength is going to be equal to the potential difference over the distance. When I get to circuits, guys, everything's going to be based around Ohm's law. V equals IR, where I is the current and R is the resistance in ohms. V is going to be the potential difference. I could also say that the power is equal to VI, so the potential difference times the current. This power formula can be written now in terms of Ohm's law, depending on what's given. If I am not given current, I is equal to V over R, so I can also write power as V squared over R. And if not given V equals IR, I could plug IR in for V, and I could say that P equals I squared R. When dealing with capacitance, guys, you'll see Q equals capacitance times potential difference. And when I'm looking at circuits also, I could say that the total resistance of a series circuit is equal to R1 plus R2 plus R3. And the total resistance of a circuit that is parallel is equal to 1 over R1 plus 1 over R2 plus 1 over R3, etc., depending on how many you are given. Guys, don't forget that you need to take the reciprocal once you do this math and find the fraction, because it's not the total resistance equals 1 over, it's 1 over the total. So when you solve for this, then you have to take the reciprocal to get this. Okay, guys, when we get to magnetic fields and forces, F equals I L B sine theta. Okay, now this is the current, the length, the magnetic field force on a wire, and the direction between the current and the magnetic field. The other one is going to be F equals Q V B sine theta. So this is charge, the velocity of the charge, and the direction of the motion and the magnetic field. For waves and optics, we know that the velocity of a wave is equal to its frequency times its wavelength. And we know that the velocity of a wave in a certain medium that is not a vacuum is equal to the speed of light divided by the index of refraction of that particular medium. I then can use those two formulas as well as Snell's law. N1 sine theta 1 equals N2 sine theta 2. That is going to be used to find the angle of refraction, which is also known as Snell's law. When I get to lenses and mirrors, I could say that 1 over F, okay, and this is not going to be frequency, so hold on one second. That is going to be equal to 1 over DO plus 1 over DI. Okay, so what this is going to be focal length. This is going to be the object distance, and this is going to be the image distance. For magnification, I could say that the magnification is equal to minus DI over DO. And if M is less than 0, the image is inverted. Next is going to be heat and thermodynamics, guys. And you might have seen a lot of this in chemistry. Q equals MC delta T. Okay, so this is the heat that's going to be added or removed, the mass, the specific heat, and if delta T is less than 0, then heat's been removed. We also need to know that Q is going to equal ML, where L is going to be the heat of transformation, or this is like for phase change. Then we got the first law of thermodynamics. The change in internal energy is equal to the heat that is added or taken away and the work done. And then we need to find the energy efficiency. That is going to be equal to the work done divided by the heat absorbed. So we see this is usually written as Q hot. So this is the heat absorbed times 100. Two more topics to go. The next one is going to be pressure and gases. You know that pressure is going to be equal to the force divided by the area. So this is going to be the force that's applied by that gas or by that liquid divided by area. And then the ideal gas law says for an ideal gas, the PV, pressure, volume, over temperature, that is going to remain constant. For modern physics students, we know that the photon energy, usually written as E photon, is going to be equal to Planck's constant times F. Sometimes you'll see Planck's constant written with a little bar through the H. It doesn't really matter that much. And we know that Ke max, and this is going to deal with the photoelectric effect, is going to be equal to HF. So Planck's constant is going to be given, guys. This is the light's frequency, and the work function is going to be subtracted from that. So this is the work function of the metal. We know that the wavelength is equal to Planck's constant over momentum. And if we look at relativistic factor, this is kind of like a hard symbol for me to draw, but it's like a weird like V. That's going to be equal to 1 over the square root of 1 minus, in parentheses, the velocity of that wave divided by c. And then don't forget about the famous one, guys, that E equals mc squared. And this is that every energy has a mass counterpart and can be converted between. So this is energy mass conversion. If there's a formula you think I missed, guys, please leave it in the comments down below. If I made a mistake, I apologize. I tried to get through it quickly. I have videos on every single one of these topics, so just look through the playlist and you'll find everything you need to know. If you have any other questions or if I did miss a topic that you would like me to do, once again, leave them in the comments below. If you like this video, got some value, give it a thumbs up so YouTube shoots it out to other people. Tell your physics friends that you found the best physics tutoring channel on the internet. And until I see you guys on the next one, stay positive. Work really, really hard out there. Please be kind to other people. I'll catch you on the next one.